In this section, we investigate special parallelograms. The first of these is the rectangle, abbreviated RECT, which is defined as follows. Definition: a rectangle is a parallelogram that has a right angle. See Figure 4.20. Any reader who is familiar with the rectangle may be confused by the fact that the preceding definition calls for only one right angle. Because a rectangle is a parallelogram by definition, the fact that a rectangle has four right angles can be easily proved by applying corollaries 4.1.3 and 4.1.5. Corollary 4.1.3. The opposite sides of a parallelogram are congruent. Corollary 4.1.5. Two consecutive angles of a parallelogram are supplementary. Corollary 4.3.1. All angles of a rectangle are right angles. The following theorem is true for rectangles, but not for parallelograms in general. Theorem 4.3.2. The diagonals of a rectangle are congruent. Complete a proof of theorem 4.3.2. The diagonals of a rectangle are congruent. Given rectangle MNPQ with diagonals segment MP and segment NQ. See Figure 4.21. Prove segment MP is congruent to segment NQ. Proof. Statements. Reasons. Statement number 1. Rectangle MNPQ with diagonals segment MP and segment NQ. Reason number 1, given. Statement number 2. MNPQ is a parallelogram. Reason number 2. By definition, a rectangle is a parallelogram with a right angle. Statement number 3. Segment MN is congruent to segment QP. Reason number 3. Opposite sides of a parallelogram are congruent. Statement number 4. Segment MQ is congruent to segment MQ. Reason number 4. Identity. Statement number 5. Angle NMQ and angle PQM are right angles. Reason 5. By corollary 4.3.1, the four angles of a rectangle are right angles. Statement number 6. Angle NMQ is congruent to angle PQM. Reason 6. All right angles are congruent. Statement number 7. Triangle NMQ is congruent to triangle PQM. Reason number 7. Side angle side. Statement number 8. Segment MP is congruent to segment NQ. Reason number 8. CPCTC. Corresponding parts of congruent triangles are congruent. All rectangles are parallelograms. Some parallelograms are rectangles, and some rectangles are squares. Definition: a square is a rectangle that has two congruent adjacent sides. See Figure 4.22. Corollary 4.3.3. All sides of a square are congruent. Because a square is a type of rectangle, it has four right angles and its diagonals are congruent. Because a square is also a parallelogram, its opposite sides are parallel. For any square, we can show that the diagonals are perpendicular. We measure area in square units. The next type of quadrilateral we consider is the rhombus. The plural of the word rhombus is rhombi. Definition: a rhombus is a parallelogram with two congruent adjacent sides. In Figure 4.23, the adjacent sides, segment AB and segment AD, of rhombus ABCD are marked congruent. Because a rhombus is a type of parallelogram, it is also necessary that segment AB be congruent to segment DC and segment AD be congruent to segment BC. Thus, we have corollary 4.3.4. Corollary 4.3.4. All sides of a rhombus are congruent. We will use corollary 4.3.4 in the proof of the following theorem. Theorem 4.3.5. The diagonals of a rhombus are perpendicular. Study the picture proof of theorem 4.3.5. In the proof, pairs of triangles are congruent by the reason side, side, side. Given rhombus ABCD with diagonals segment AC and segment DB. See Figure 4.24a. Prove segment AC is perpendicular to segment DB. Proof: fold triangle ABC across segment AC to coincide with triangle CAD. See Figure 4.24b. Now fold triangle CED across half diagonal segment DE to coincide with triangle AED. See Figure 4.24c. The four congruent triangles formed in Figure 4.24c can be unwrapped to return rhombus ABCD of Figure 4.24a. With four congruent right angles at vertex E, we see that segment AC is perpendicular to segment DB. An alternative definition of square is: a square is a rhombus whose adjacent sides form a right angle. Therefore, a further property of a square is that its diagonals are perpendicular. The Pythagorean theorem, which deals with right triangles, is also useful in applications involving quadrilaterals that have right angles. In antiquity, the Pythagorean theorem claimed that the square upon the hypotenuse equals the sum of the squares upon the legs of the right triangle. See Figure 4.25a. This interpretation involves the area concept. Our interpretation of the Pythagorean theorem uses number or length relationships. See Figure 4.25b. By counting squares in Figure 4.25a, one sees that 25 square units is the sum of 9 and 16 square units. When right angle relationships exist in quadrilaterals, we can often apply the rule of Pythagoras. The Pythagorean theorem: in a right triangle with hypotenuse of length C and legs of lengths A and B, it follows that C squared equals A squared plus B squared. Provided that the lengths of two of the sides of a right triangle are known, the Pythagorean theorem can be applied to determine the length of the third side. In example 3, we seek the length of the hypotenuse in a right triangle, whose lengths of legs are known. When we are using the Pythagorean theorem, C must represent the length of the hypotenuse. However, either leg can be chosen for length A or B. What is the length of the hypotenuse of a right triangle whose legs measure 6 inches and 8 inches? See Figure 4.26. Solution: C squared equals A squared plus B squared. C squared equals 6 squared plus 8 squared. C squared equals 36 plus 64. C squared equals 100. C equals 10 inches.